Hello, we are Mike Robinette, Ray Tiffin, Jackson Lipford, and Joao Franco, and we want to share our project, which explores the dynamics of complex or internally held and simple expressed beliefs, a contagion-based modeling approach to explore the dynamics between expressed and internal beliefs. We're going to go through the motivation for this project, key societal assumptions, modeling assumptions, and then we're going to look at the two approaches we took in modeling this, so mean field approximations and simulations, and then we're going to look at our preliminary simulation results. So our motivation in this project, belief dynamics defined as how beliefs form and evolve, and their historic modeling approaches have not yet reconciled sudden shifts in observed or publicly expressed beliefs despite inertia in updating privately held or internal beliefs. So this motivates the question for us. What if individuals express beliefs that differ from ones they truly hold? We hypothesize that social pressure drives outward conformity even when internal beliefs differ. The key societal assumptions we're holding in these models is pretty simple. It's just that people will express beliefs outwardly that do not authentically express their inwardly held beliefs. Our modeling assumptions, populations discuss a single topic on a fully connected or Erdos-Renyi network. Individuals hold binary beliefs. They're either for or against, with possible differences between internal and expressed beliefs, which we'll show that in more detail in upcoming slides. Beliefs update simultaneously on the network. Internal beliefs follow complex contagion. Expressed beliefs follow simple contagion. And with that, I'm going to hand it off to Joao Franco to discuss the mean field approximations.
Based on the modeling assumptions previously described, we designed our mean field approximations. First, we started by a simple toy model where only expressed beliefs can change. So as my colleague mentioned, internal beliefs and external beliefs can be A, if against, or F, if in favor. So on the left-hand side, we see that a person that holds opinion belief A, but express F, meaning it's a AF, it can only go to AA, meaning changing from in favor to against regarding expressed beliefs. The same applies to the ones that held in favor beliefs. Nonetheless, when we define the ordinary differential equations, a person that expresses F can be impacted by AA or FA. Within the ordinary differential equations, other parameters are included. For example, parameter K mentions the number of people or the context per time period that impact belief dynamics. If K equals 1, expressed beliefs will follow a simple contagion model. If greater than 1, one's beliefs is impacted only when consensus is observed in a group of more than one person, of K people, and so it reaches a complex dynamics. We also have beta, which is the probability of a person meeting with another group or another individual, or another K individuals. If beta is 1, we have a fully connected network, and if beta is different from 1, we have a Erdos-Renyi network. So on the next slide, we make the simulations for a fully connected network and for a simple contagions model regarding expressed beliefs. In the top and inside, we see a case where the different states that a person can hold, so AF, FF, AA, or FA, where AF corresponds to individual holding A but expressing F, we see that over time, on the right-hand side, the share of people that express A, so it's A observed, it's constant over time, as well as the people that truly held A. What it seems to happen is that over time, the proportions within each macro group of observed or expressed and true, pardon, changes over time. So for example, on the left-hand side, people that held A but express F decreases, while at the same time, the people that hold A but also express A increases, maintaining the overall trend on the right-hand side. In the bottom, when we focus on more extreme cases where no coherence between beliefs or people with coherence between holded internal and expressed beliefs exist, we see a more extreme variation, but in the end, the overall trend goes towards equal share of all states. We tried these cases with opposing shares of AF, FF, AA, and FA, giving more emphasis to people that are coherent between express and internal, or vice versa, and the overall dynamics don't change. So we started in the next slide, we showcase a more complicated case where not only expressed beliefs can change, but also internal ones. As we see in the left-hand side, a person that holds A but expresses F only changes their internal belief to F if after three consecutive rounds where they see consensus around them. On the right-hand side, we have the respective ordinary differential equations that are somehow more complicated and that they are currently being implemented to see the overall dynamics of the model. So now my colleague in the next slide will show more detail our modeling approach when following simulations.
Okay, so I'm going to talk through the rules of the simulation model. So a node can be in one of four states. Aligned red, that's just where external and internal are equally aligned. Same for blue. We have conforming red, where outwardly we express red when really inwardly we hold blue. And then we have the opposite of that. We update external state through simple contagion as follows. We're looking at this from the perspective of the blue node. So we will randomly select one of blue's neighbors, and if we will adopt that neighbor's externally held state, which we can see over here to the right. Next, we will look at how a node updates its internal state, which is through complex contagion. For this, we leverage the idea of consensus, which is simply defined as the state. It's when the state of external beliefs are aligned across the board. So when that is true, when we have consensus across 3 iterations, the node will update its internal state. And with that, I'm going to let Jackson Lipford talk through our results.
Awesome. Thank you, Michael. So let's start looking at the fully connected Erdős-Rényi network using our simple contagion model. On screen, you can see 3 custom network measures that we coded up to track the simulation. On the left is just the count of nodes in all 4 states. In the middle is the count of liars and non-liars, liars being externally expressing a belief differing from the one they hold internally. And on the right, we have alignment over time, which is a node's internal state mapped to the external state of its neighbors and how much in alignment they are. So as you can see, things are a little bit messy. After 50 iterations, no clear winner emerges. Liars and non-liars occur in roughly equal proportion, and alignment over time varies ever so slightly around 50%. Now, let's see how these models play out over a different network. Next slide, please. So here, we're using a network created from the 6th book in the Game of Thrones series, and it has a high small world coefficient. As you can see, the simple contagion model produces very similar results to the Erdős-Rényi network. No alignment and no clear winners. Now, those are our results for simple contagion, but we have one more model that we wanted to try. Next slide, please. We also wanted to explore what would happen if nodes looked at their entire neighborhoods when selecting their external state, rather than just a single random neighbor. In this model, a node will set its external state to match the majority state of its neighbors. Next slide, please. When using this model, things move very fast on the Erdős-Rényi network. By the fourth iteration, the network has already arrived at full consensus, and the aligned red nodes have prevailed, leading to an early stoppage of the model. Next slide, please. When we try this on the Game of Thrones network, we see more variability in node states as the network approaches equilibrium. Complex contagion seems to produce a higher alignment value as well as more nodes outcompeting other states. And with that, I'll turn it back to Michael.
That's a wrap for our project. Thank you for your attention, and hopefully your inwardly held beliefs are reflected on the outside. Thanks.